Good morning, good afternoon, good evening, everyone joining from wherever you are joining. So what we'll talk about today in this presentation is the KPIs regarding electrical machines. So we've seen in Dan's presentation what the importance of electrical machines in various applications and various systems are. And we've also seen the requirements for the different industries that we have. So what we'll see in this presentation is more to do with the different KPIs that we have when designing the machine, so that we can improve the overall performance and also the efficiency through a simulation of electrical machines. So just a very general overview of the different areas of interest that we'll be looking at today. So we'll look at the modeling of electrical machines, the design, how we go about doing that, what different tools we have to do that. And also the main focus will be on electromagnetic performance of the machine, the different KPIs related to that. And then we'll touch very briefly on some other multiphysics subjects like noise and vibration and thermal analysis. So the tools that we have, the EMAG or electromagnetics tool that we have to do those different things are mainly CST Studio Suite, Opera. We also have CST connected to the platform, which you can use to exchange models very easily. And we also have the new app on the platform, which is called the Electromagnetic Electrical Machines Analysis. So just a brief overview of what we'll be going through during this presentation. So first of all, the modeling, and then a deeper dive into the electromagnetic analysis and the related KPIs. And then we'll go through the design optimization, reduced order modeling, and then briefly touch on the multiphysics aspect. So to start with modeling of electrical machines, so what we really require essentially is to have a reliable CAD model that can be used for easily creating the model and easily manipulating the model, exchanging data between, or exchanging the CAD model between different software, not only electromagnetics, but it has to be easily imported and exported from our electromagnetic software to other physics software. And also the models need to be easily parameterized, and we need to have easy meshing. So to do that in our EMAG solutions, we have from very basic or very simple modeling to very intricate modeling of the design. We also have templated designs for electrical machines, whether it's with Opera or with CST, where you can just input the dimensions of your electrical machine, and then the whole model would be done automatically by the software. And then the analysis will also be done. There are different types of analysis that are already there, which you can choose from. And importing, exporting of the model of the CAD model under different formats, CAD formats. And parameterization of the model, which is also very easy to do for different dimensions, or even for different parameters that you want in the machine, and easy meshing. We also have the modeling that's available through the platform. We can also use CST connected to the platform to exchange the models, but we can also use the electrical machines analysis app on the platform to do the same job, that is from creating the geometry, parameterizing the model, assigning different materials, and everything that's got to do with the setup of the machine. Next up is the electromagnetic analysis of the machine. So first of all, why do we want to do an electromagnetic analysis of the machine? The main reason most of the time is to achieve the desired torque and power of the machine according to the specification sheet that we have, the requirements that we have for a specific motor design. To do that, we normally start from doing no load or load and load analysis. And we also have mechanical coupling, perturbations, depending on the type of motor that we're looking at. And the main so the most important thing is to maximize efficiency, as you can imagine, so that you have a better performance over the whole operating range of the machine. So for a no-load simulation, for example, we have two important aspects that we look at. So the first one is the cogging torque. Cogging torque, which is mainly looked at for permanent magnet motors. And this reducing the cogging torque helps to reduce the noise and vibration in the machine, and also to reduce the power losses and put less stress on the structural model of the machine. So like I said, this applies mainly to the permanent magnet machines, but more generally to all types of machines. We look at the electromotive force, or the EMF. So for motors, for example, this is very important to determine the type of supply or the supply rating that we'll be using. And for generators, we'll be using that to maximize the EMF so that we have a maximum output voltage for a specific model. So for example, we can directly look at the cogging torque characteristics or EMF characteristics in the machine through bespoke or customized analysis, or analysis that are already automatically available. Next one for load simulation. So there are a number of things that we look at usually for a load simulation, but the first thing would be to have an optimized load angle. So when we say optimized load angle, this is to obtain the maximum torque of the machine at a given current. And we have tools, we have features to do that automatically in CST as well as in Opera, so that you can, so you can use those to calculate the optimized load angle, and you don't have to do that manually, which can be time consuming for a lot of times. And also we have we need to look at the torque waveforms, whether it's the average torque to maximize the average torque, or minimize the torque ripple. So the torque ripple which contributes to the noise and vibration and losses of the machine as well, just like cogging torque would do. And also the harmonics of the torque waveform. So for example, the 6 and 12 harmonics, which normally contribute to the noise and vibration as well. So looking at that and reducing that would reduce the noise. So for the electrical outputs, we also like to look at the voltage or current waveforms from the windings, from the stator windings. So normally it's very important to look at those just to make sure we have correct outputs, we don't have any faults in the machine, or we have the three-phase supply, which is 120 degrees out of phase, for example, which is needed, and just to make sure everything is fine on the winding side. And also inductance calculation, which is very important, which can affect also the current waveforms, and which can affect the flux distribution in the machine. We also look at the losses, which is very important in the machine design, which we'll see the importance just a bit later. But the different types of that's for the inductance. So the different types of losses that we have in a machine. Normally we have the iron losses, which occurs in the steel laminations. That can be in terms of induced eddy currents, or that can be hysteretic losses as well, due to the change in flux direction while the machine is rotating. And we can also have eddy currents in the magnets and ohmic losses in the windings, whether it is stator windings, or sometimes we have motors with windings at the rotor. So we can also look at the ohmic losses in the rotor windings. Another important aspect is the mechanical load on the machine. So first one is the mechanical coupling, where we want to simulate a mechanical load. This is very important because simulating a mechanical load would allow you to look at the output torque and currents versus time. And also the centrifugal load on the rotor of the machine, for example. This will cause a stress on the rotor, and we want to simulate that at a specific speed. And from that, we also want to get the deformations that it causes to the rotor. So when I say deformations, this can be translated to displacements in the geometry or in the machine itself. And we also have a nice feature where we can look at those very small displacements by moving the mesh or moving the nodes of the mesh of the model. You can think of, well, you can say that we can redo the geometry, but if you redo the geometry, the very small changes with respect to the displacement will really get lost in the numerical error, if you like. So that's why it's very important to be able to move the mesh and then look at the effect of those displacements on the electromagnetic forces or electromagnetic KPIs in general. So for the perturbation analysis, so we mainly talk about concentric and eccentric machine cases. So a concentric machine case would be where the stator axis and the rotor axis, as well as the center of rotation, are all aligned, and the machine is rotating concentrically in a normal way, in an ideal way. But most of the time, this is not the case. So this could be due to many different reasons, like manufacturing defects, or when the motor is, for example, put on the drivetrain. Different things can cause the machine to be non-concentric or eccentric in that case. So we have different types of eccentricity. The very basic one or common one, first one would be static eccentricity. So for example, where you have the rotor axis and the center of rotation that are aligned, but they are misaligned with the stator axis, which means that the rotor will still rotate around the center of rotation, but you can see that you don't have a very uniform air gap all around the rotor. Nevertheless, the rotor, the air gap will still stay constant with time. Whereas for a dynamic eccentricity model, you have the stator axis and the center of rotation that are aligned, but they are misaligned with the rotor axis. When I say misaligned here, we're looking at a 2D model, so we can say that they are in parallel, for example. So the rotor axis will rotate around the center of rotation, which means that, which you can see in yellow here, the air gap will not remain constant with time. So because it will keep moving around. And another case is, which is for a 3D case, is the rotor tilt, where the rotor can be tilted in any direction on the actual length. And this can cause different types of eccentricities, like forward whirl or backward whirl, for example. And so those eccentricities need to be also modeled through moving meshes. So what we have in Opera is using so moving the nodes of the mesh, so that we can look at so we can do a sensitivity analysis and look at the effect of those displacements or those deformations on the electromagnetic parameters. So next one is the DQ model. So what is a DQ model? It's simply a mathematical representation of the behavior of the machine, a simplified version, where we convert the three-phase AC frame into a DC frame. So for example, in a three-phase machine, you would normally have currents like IA, IB, IC. But it makes it a bit more difficult to control. So what we do is convert the IA, IB, IC sinusoidal waveforms into DC, ID, and IQ current, which makes it much easier to control and much simpler to calculate for operating range of the machine, for example. So the main importance of a DQ model is to have a better control of the torque in the machine and also in the flux. And another important point is efficient inverter control. So to set up the DQ model, it's very easily done in CSD. So you can use the drive scenario features that are available and then create your DQ model from there. All you need to do is enter your various parameters like load angle, current values, and time samples, number of samples that you want. And then from there, you can have the different outputs like torque versus current, load angle versus current, torque and load angle in terms as a function of current, like you can see a nice diagram here relating all the three. So this will be used later in the dynamic characteristics or dynamic characterization of the machine. So talking about the dynamic analysis of the machine, what we mainly look at in this is the torque versus speed analysis. So that is normally for the whole range, for the whole operating range of the machine. And from there, we can also deduce the efficiency map of over that range, which also requires very detailed loss calculation of the machine in different parts, so that we can have the power over power input, power output, efficiency, and any other parameter at all the operating points of the machine. So we can again do that in CSD very easily. So we've got a feature for that for the drive scenario as PMSM loss map, for example. So all you need to do is use the DQ model that you've already created with the same feature or drive scenario, and then use that to calculate the losses. And from there, you can have the power as a function of speed. And also you'll have the different losses that occur or the ID current, ID and IQ current in terms of the torque and speed, and the different losses that occur in the machine as a function to create the efficiency map. Sorry. So another important aspect when simulating electrical machines is demagnetization. So that is mainly with when you have permanent magnets in your machine that can be demagnetized. So there are many reasons why that can happen. So the main reason would be at high temperatures, you can have demagnetization, but also if you have a field opposing the magnetization direction, for example, of your permanent magnet, that can occur as well. And also when there are structural deformations or shocks in your on your permanent magnet or in the machine in general. But we mainly look at high temperature situation and an opposing field in the machine. So the KPIs in this case would be to maximize the efficiency, or to look at what effect it has on the efficiency of the machine, and also to know what sort of voltage reduction we have in case of faults or in case of demagnetization. So in Opera, we have we can use the demagnetization model. So this is done by reading in a table of values, which you can use, for example, to create a function of demagnetization in terms of the flux density, the temperature, or whatever values that you have in your table, and then you include that in your model, and this can, you can use that to model the demagnetization. And once you have that, so you can also look at the faults that occur with respect to demagnetization of your permanent magnets in your motor. So the worst case would be when you have a current amplitude that's applied in the negative d-axis or in the other direction of the magnetization of your magnet, and that causes a maximal demagnetization. So you can see here, for example, we have a voltage reduction. So that comes from the fault that occurs at a specific point in the machine, and then you can compare with the initial waveform and see the voltage reduction in your windings. So next one is the design optimization. So design optimization has become very common over the last years for electrical machines in general, but also for other applications. What we always strive towards is better performance, higher efficiency, and also reduced costs in general terms. So what we can do with optimization, so normally we'd use geometric designs as variable, but we can also use any other input parameters as variables, and then as objective functions we can use any of the outputs that we've discussed earlier, like, for example, average torque, maximizing the average torque, minimizing the torque ripple, flux density in different regions of your machine as objectives and constraints. And from there, we can obtain a Pareto front, which is very useful, where you have the different optimized models. And from the different optimized models, you can make a more informed decision on what model to use, in which case, depending on the specification sheets requirement. And you can also use surface response to create a design from a design of experiment that you've created, and also design space exploration. So there are various ways to optimize your models of electrical machines. So we can use the CST optimizer, for example. We have the Opera optimizer, but we also have EyeSight or a process composer that can be coupled to both CST and Opera. So the good thing about EyeSight and process composer is that we can make use more of the results analytics and the post-processing features that we have for optimization, which are very nice and more specific to optimization. So reduced order modeling is something that has also become very popular in the past years. Mainly when you have to exchange data between different physics, when you're looking at the multi-physics system. So reduced order modeling is really a simpler or reduced representation of a model by using a mathematical expression, but you can also use functional mockup units or FMUs that are available in CST. And also in EyeSight, so the optimization that we've seen just before. So we can make good use of that in a multi-physics setting, and also optimal exchange between the various, optimal exchange of data between the various physics. One nice feature that we have in CST is the reduced order model authoring, where you can easily create your, so from the DQ model or loss map model that you've already created, or the different drive scenarios that you've used, you can then create a reduced order model and then have specific inputs and outputs to that reduced order model. You can also use iSight and Process Composer for that, coupled with the CST or Opera. It is a slightly more involved process, but the biggest advantage is that it is very flexible in terms of the inputs and outputs that you can use in that model. And also you can make use of the surface approximation methods that are available from iSight or Process Composer. So for example, here I'm showing a mathematical expression that was derived for a torque average, like you can see here, which is easily reused. Like one equation is very easily executed in Python, for example, and that can be very nicely integrated with any other physics. And here is just to show an example of the results from a reduced order model predicted here as compared to the finite element models, which you can see it's very, very close. So last one is the multi-phase simulation. I will go very briefly on that, but it's just to show the other capabilities that we have and what we can do from an electromagnetic simulation. So assuming that we've already done our electromagnetic simulation, loss calculation, and so on, where do we go from there? So the next thing is we can create the reduced order model, create our FMU, and then integrate that on a system level. So for example, we can use Daimola or any other products to do that. And from there, we can obtain the desired waveforms. And from the waveforms, those can be used in other physics, in other multiphysics calculations like thermal, CFD, or NVH analysis. So just a brief word on control system. So once we have the FMU derived from CST, for example, we can easily integrate that into our system level. For example, when we have the controller so we can use the operating points from the FMU here and then input that into the controller, or also for the machine on the system level. And thermal simulation, which is also a very important aspect. So temperature rise comes from, well, a lot of the temperature rise comes from the electromagnetic losses that occur in the machine that can cause various different problems, like the magnetization of magnets, which we've seen earlier, can also cause structural deformation, winding, and insulation problems. And so with the tools that we have, we can easily pass the electromagnetic losses to the thermal solver. And also noise and vibration analysis. So electromagnetic forces are very often converted or translated or cause vibration, I should say instead. And those vibrations are transferred to the drivetrain. That can cause multiple problems. So for example, it can cause discomfort in the electric vehicle if we are simulating an electrical machine for an electric vehicle, and also it can cause noise in the machine and on the whole drivetrain. So just to conclude very quickly, we've looked at the different KPIs when designing and simulating an electrical machine with our electromagnetic solutions. So mainly modeling, electromagnetic analysis, optimization, reduced order modeling, and multi-phase analysis. and all the electromagnetic tools that we have cover all of this, so that you can make your simulation more efficient and also your machine more efficient, faster and more reliable. Thank you for your attention.